Right, over here I have a whole load of functions and what their antiderivatives look like. Some we've talked about, some we haven't. So just going to talk through these guys. You don't need to frantically write this down, at least I suggest that you don't. Why don't you wait till the video comes out or take a picture of it? I'll get my hand out of the way. And you can write it down when you've got time. So let's talk through each one of them in turn. If you've got a function like 5x squared or 4x to the negative 2 or 3x to the half, anything that contains a power of x, right? Then you can use this rule, which is called the power rule. And this is what it looks like algebraically, but I tend to say this English. Add 1 to the power, that's the n plus 1 bit, and divide by the new power. So that's the power rule. So that allows us to find antiderivatives of 5x cubed plus 2x, things like that. The antiderivative of 1 over x is log x, the natural log of x. I like this one. The antiderivative of e to the x is just e to the x. The antiderivative of a sine is a negative cosine, and the antiderivative of a cosine is a positive sine. I can't remember if we did this one, but now I'm doing it if we haven't. Do you know that the antiderivative of secant squared is tan? Hide these guys. So if you ever have to find the antiderivative of a tan, a secant squared, the answer will be a tan. Okay, what is the antiderivative of secant tan? Anybody know it? Think back to Calc 1. You differentiated something and the answer ended up being secant tan. So that's the guy you want. The guy you started with that would do that. Any guesses? Any ideas?
But just secant?
There you go. It's secant. What's the antiderivative of 1 plus x squared? Also written as 1 over x squared plus 1. It's the same thing. Remember that one?
What was it one more time?
1 over 1 plus x squared. This guy here. Last few seconds, going to tell you if nobody can say it. Inverse tan. How about 1 over the square root of 1 minus x squared? That's also an inverse trig. Any guesstimates on what that might be?
Cosine?
Inverse sine.
Inverse sine. If you stick a negative 1 on the top, it's inverse cosine. I'll just show you the last one because I strongly suspect you've hardly ever seen this one. This one represents things like 2 to the power of x, 5 to the power of x. You won't see it very often, but when you do see it, you need to know what its antiderivative is. So any number, a to the power of x, its antiderivative is a to the power of x, all divided by the natural log of whatever it is. So 5 to the x would get you 5 to the x divided by the log of 5, for example. All of these guys have the classic plus c added on. And these are, for the most part, the most common things that you need to know what the antiderivative of them is, right? Now, quite a lot of these, pretty much everything except the first one, aren't they sheer memory? It's just like learning the language, you know? This is the word in English, what is it? What's the same thing in French, right? Right, this is the fx, what is the antiderivative? And you just have to have a good memory. People practice these in different ways. Some people do a little card where on one side they put f of x, on the other side they put the antiderivative, and they kind of shuffle the cards and they randomly pick it up and say, okay, what's that one? Yep, I was right. Or, oh God, I forgot that one again. And, you know, you work on it until it's in your brain. Going to use these a lot today. So Next section. We are going to look at section 5.3. And it's got a really interesting name called the Fundamental Theorem of Calculus. Actually, it has a little bit at the end, part 2. Sounds like a movie, the second episode or whatever. The Fundamental Theorem of Calculus, part 2. What that is going to do is that is going to allow us to find the exact answer to the area under a curve. So let's show you what that theory or theorem looks like. Imagine that you have got a normal curve y equals f of x. And this curve starts at this guy here, which is what x equals a, finishes up here at x equals b, and we want to find the exact area under the curve, right? We want to find that guy. Now, the techniques that we have been employing for the last week have been very boring and very time consuming. Wouldn't you estimate it by splitting up into 4 strips or 24 strips and doing a T4 or an S4 or a midpoint 4? But all of those are just estimates, right? They're not perfect. They're just, you know, some are better than others, but they're still estimates. And we did one example where we did that limit as n tends to infinity. And God, that thing would take about half an hour if you had to do it that way every single question. So that's not really a candidate. So what does the Fundamental Theorem of Calculus Part 2 say? Well, let me write it down for you so I get the pen I want to use. There's one other pen. Okay, I'll use this one. The area under the curve. And we're going to use that notation, right? So that just means the area under the curve from x equals a to x equals b of this function. So this here is basically telling us to find that. According to the Fundamental Theorem of Calculus, it's that where capital F of x is the antiderivative of f of x. And that is amazing. All you need to do then is find the antiderivative of the function, evaluate it at b, right? Find out what it's equal to at b, evaluate it at a, and subtract. So let's show you a very quick example of how easy it is to do. Suppose I want to know the area under the curve from 0 to 2 of x squared. Okay, imagine what that might look like. Right? Looks something like that. Now, I'll show you the way that we tend to set out the working for this. First thing you're going to do is the antiderivative of x squared. Now, that's a power rule, isn't it? So you add 1 to the power, and then you divide by the new power. And then you draw a vertical line, and you write x equals 0 to x equals 2. And then you plug in 2, which is essentially what that guy would be. Take away, you plug in 0, which is what that guy would be. 2, 4, that's 8/3. Take away nothing, boom. If I hadn't been doing a lot of talking, that question would have probably taken 1 minute. And that's not an estimate for this area. That is the exact answer, right? It's about 2 1/3. That is really cool, right? Really smooth, really nice. Right, let's try another one. Suppose I wanted to find the area from 1 to 4 of 6x squared plus 2x plus 1. I'm going to mute you right now because I'm getting some feedback. Might be distracting to you as well. Okay, so let's go back in the discussion. Here we go. Antiderivative. Add 1 to the power. Divide by the new power. Add 1 to the power. Divide by the new power. What will the number 1 get me when I write its antiderivative?
X.
Yeah.
1x.
Agreed. And then you do evaluated at x equals 1 to 4. So think of that vertical line as the word evaluated at, right? So there's the fella, evaluated at x equals 1 and 4. So it's going to be 2 times 4 cubed plus 4 squared plus 4. Take away 2 lots of 1 cubed plus 1 squared plus 1. 4, 16, 64, double 64, 128. Add 16, add 4. This is a bit easier to do. 2 add 1, add 1. 20, 168, take away 4. I get the answer 164. So by this fundamental theorem of calculus part 2, we can find the exact area under any curve, starting at any number you like and ending at any number you like. And it essentially involves find the antiderivative and then evaluate these two numbers. Big one, take away little one, right? F of B, take away F of A. So it doesn't require an awful lot of thought, right? It's pretty easy to remember what you have to do. So the devil is going to be in the detail, and that is finding antiderivatives of these guys. Now, these were pretty straightforward, right? They were just power rules, nice old numbers. So you know that's not going to last forever. So this one is a bit like question 1 from your homework. And it's going to be the integral from 1 to 8 of the cube root of x. Now, if you can remember what we did last Thursday, if you want to find the antiderivative, don't you sometimes have to rearrange the way something's written to make it possible? Right now, cube root is bad news. Can someone tell me another way to write the cube root of x that's going to allow me to use the power rule?
X to the power of 1/2.
If it was a square root, 1/2, since it's a cube
Oh,
root,
cube
just
root, 1/3.
1/3, right? We cool with that? Now, power rule works whether that number is 2 or 22. It works if it's a half or a third. It even works if it's -2 or -1/3, right? Doesn't really care. The power rule is quite versatile. So I'm going to add 1 to the power, which is 4/3. I'm going to divide by that new power. Well, dividing by 4/3 is the same as finding 3/4. And then we're going to evaluate it at x equals 1 to x equals 8. Fair enough. Since we want exact values, you need to do style points. And style points mean make it look like this, Ella. Well, 4/3 is the cube root of x to the power of 4. Okay, now that's going to be 3/4 the cube root of 8 to the power of 4. Take away 3/4 the cube root of 1 to the power of 4. That guy is pretty massively ugly. So I want to show you a little trick that you can do when you're trying to do cube roots or square roots of really awkward numbers. The cube root of 8 to the power of 4 can be redone as the cube root of 8 to the power of 4. In other words, switch places with the power and the cube root. But the cube root of 8 is easy. It's 2. So it's 2 to the power of 4. So 2, 4, 8, 16. So this is 3/4 of 16. Take away 3/4 of 1, which is still 3/4. So that's just a little trick of the trade when you've got really awkward cube roots or square roots. Sometimes it's better to do the square root cube root bit first and then, cube the answer or whatever. Now this guy here, I believe, gets you 12. Take away 3/4. This is 11 1/4, which is not the right answer. It's 45/4, which is the correct answer, because all math exact values have to be written down as improper fractions. You don't do mixed fractions. We don't like them. Are we okay with that question? The awkward numbers, but it's still basically antiderivative evaluated at 2 places and subtracted. Let's change the letter. This is a bit like question 5. Actually, that's not like 1, that's like 4. So this is like question 5. The integral from 0 to 2. Okay. It's not a big difference. Isn't this just the variable is going to be u instead of x? Right, so don't let that bug you. It's not a big deal. What's more important is this is not ready to be used as a power rule. Agreed? Just not ready. So what should I do to get it ready?
FOIL.
Agreed. I'll cut out some corners here. You can check it later, but I believe that's what you eventually get when you do FOIL. At this point here, aren't we ready to do the power rule? So add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. And now it's going to be u equals 0 to u equals 2. If you plug in 2, you get 1/3 times 2 cubed plus 3 lots of 2 squared. Take away 7 times 2 minus. Okay, here's another trick of the trade. If you know that one of these numbers, especially when the thing is a u, if you know all of this is just going to be 0, can't you just write down take away 0 without writing 1/3 0 cubed plus 3 lots of 0 squared and so on? Now, this fella is going to be 8/3. This guy's going to be 12, and this guy's going to be take away 14 minus nothing doesn't do anything. -2, and that guy is 6/3, I believe. You can check it later. I believe the final answer is just 2/3. Are you okay with that one? Sometimes you have to FOIL. How about this one? Again, I need a power rule. I can't do a power rule like this. I got to get it, fixed so that we can, we can deal with it. What could I do?
Change the square root of t to the 1/2.
I like the thinking. Yes, you do that. You're right. What do I do next?
Distribute.
Okay. T to the half times 2 gets me 2t to the half. This guy times this guy gets me 3/2. 1 1/2 is 3/2, right? Now, power rule. If you add 1 to this guy, you get 3/2. Dividing by 3/2 is like multiplying by 2/3. That's why that became 4/3. Add 1 to this guy, you get 5/2. Divide by 5/2 is the same as multiplying by 2/5. And then you're going to evaluate at 0 and 9. Now I'm going to do style points. This guy is going to be 4/3 the square root of t cubed, take away 2/5 the square root of t to the power of 5. So make it look like the original, right? The original had some square roots in it. I should have square roots. Now you plug in t equals 9, you get that guy, take away that guy. Oops, that's a 5. And can I do that, take away nothing again to save some time? Because when you plug 0 in here and here, the whole thing's still 0. Now, if I wanted to do the exact value of the square root of 9 cubed, I guess I could multiply 9 times 9 times 9 and then go looking for the square root of it. Or couldn't I do the square root of 9 first and then cube the answer? And the square root of 9 I know is 3, and 3 cubed is 27. So that's why this guy becomes 4/3 times 27. Now the other one is that fella, and that's the square root of 9 raised to the power of 5, which is 3 to the power of 5, which is 243. And I am rapidly reaching the point where I don't want to do it in my head anymore. So I'm going to let the calculator finish this off. So what do I have? I have 4/3 of 27, which I actually could do without the calculator, but there we are. 4 divided by 3 and then times it by 27, which is that guy. Take away 2/5 times 243, which is that guy. There's an ugly looking answer, but you hit math button, choice 1, and with a bit of luck, there you go. Negative 506/5. I find, isn't it much safer if you let the calculator figure out what one of these weird things is rather than me try to do it by hand or doing it in my head or whatever?
I didn't even know that you could do that. That is really helpful.
Okay, well, we've learned something cool today. I always like that. Are we good? Any questions so far then? Are we comfortable about finding the exact value for an area under a curve between any two given numbers, which is what essentially is happening. I got a thumbs up, I like that. So I'm now going to show you an example, actually a couple of examples of some questions. Where's my little table? I need my little table, here we go. Yeah, that's too easy. Let me do a different one. So there are going to be two distinct problems with this question. The first one is the antiderivative issue. And the reason I kept this here is this guy is one of these. What is the antiderivative of 4 over 1 plus x squared?
For
So this
inverse.
Doesn't the 4 just mean you get 4 of them? You know, if that was 10, you get 10 of them, right? That's all the 4 does. So that's the first problem. The second one is when you start putting in the numbers. We need to find out the exact value of that. And you're not allowed to go and just use your calculator, because what your calculator is going to tell you is the answer is, well, I don't know, 0.12345. It's just going to give you a decimal. Exact values shouldn't have decimals. Exact values should be things like pi over 4 and root 3 and root 2 plus 1, right? It should have things like that in it, not 1.234 kind of look. So do a little squiggly line here. I need to find out what the inverse tan of 1 is. In English, that is what angle has a tangent of 1. Who have we got here? Inverse tan of 1. What angle gives you a tangent of 1? So this is trig 142. What angle gives you a tangent of 1?
Is that 180?
Well, no, that's the short answer. It's not that one. Secondly, the angles need to be in radians. So it would have been pi that you'd have said. It's
So
not
pi.
that one.
Oh, okay.
But it's not that one. But I like your thought that you're trying to figure it out. Okay. Thought that might happen. Side issue then. To be able to find the exact value for sines, cosines, tangents, inverse sine, inverse cosine, and inverse tangent, you're going to have to know a little bit about how to find exact answers. There are two ways to do this. Can you remember your big circle, your unit circle, with all the information in it? That's one way to do it. I'm now going to show you another way in which you can do that. What you need to do is you need to remember these two triangles. Let's show you the first one. It's a right angle triangle where 2 of the sides are 1 and the hypotenuse is root 2. And when you do this particular triangle, it's going to give us pi upon 4, pi upon 4. It's going to give us information about the angle pi upon 4. Now, for example, if I wanted to find the tangent, just the normal tangent of pi upon 4, isn't it, according to SOHCAHTOA, opposite over adjacent? And in this case, it's 1. So what angle has a tangent of 1? Pi upon 4 has a tangent of 1. So 4 inverse tans of 1 become 4 pi upon 4s, which simplifies down to pi. Now the second triangle, oh, by the way, this triangle you can use to get the exact value of sines and cosines as well. And then there's a second triangle that looks a bit like this fella. And it's 1, 2, root 3. And this triangle will tell you everything you need to know about the angle pi upon 3 and pi upon 6. So one of these two angles gives you a tangent of 1 over root 3. Which one of those two, because that's only two you need to pick from, which one of these two angles will give you a tangent that's 1 over root 3?
Said 1 over root 3. That'd be
Yeah.
pi over 3.
Is it?
Or opposite over adjacent. Sorry.
Okay.
Pi over
Okay.
6.
Pi over 6. Now, opposite is in relationship to the angle. So from pi upon 6 perspective, this is the opposite and this is the adjacent. 1 over root 3. We have found that guy. So it's take away 4 times pi upon 6, which ends up being simplified down to 2/3, which means that the final answer is 1/3, or as you might see it sometimes written as pi upon 3. So the area under this particular curve is actually 1/3 pi. Now, before the fundamental of theorem of calculus came by, the best we could do would be to estimate that. And I don't think many of you would actually guess that the answer was 1/3 pi. I certainly wouldn't have guessed it. In fact, when you look at this, there isn't even a sine or a cosine or a tangent or anything, right? There isn't any indication there that your answer is going to have anything to do with triangles, yet it is. So if you use this triangle, well, let's show you how I can use it. Suppose I wanted to know the exact value, a different question, but I wanted to know the exact value of sine pi upon 3. According to SOHCAHTOA, what is the sine of an angle?
That's the opposite over hypotenuse.
Agreed. So opposite over hypotenuse. In this case, the opposite is 1 and the hypotenuse is 2. So if you needed to find the exact value of the sine of pi over 3, it's 1/2. Suppose you wanted to find the cosine of pi upon 3. That's possible. Well, that's adjacent over the hypotenuse. And that's going to get you root 3 upon 2. Suppose I need to find the secant of pi upon 3. There is a direct connection between a cosine and a secant. Can you remember what the relationship is? What is a secant compared to a cosine? What's the connection?
It's the hypotenuse over the adjacent.
Right, so you just take the reciprocal. And if you want to make it look pretty, there's a secant. So do you see that these triangles have inside them every sine, cosine, tangent, secant, cosecant, cotangent, every inverse sine, cosine, tan that you could ever want? At least all the angles in the first quadrant, which tends to be where most of the questions live. And so there's just an alternate to using your unit circle and just memorizing your unit circle. It's not different information, it's exact same information, just in a different format. Put that back for a second. Are we okay with that? Now, that was a little side issue, but you sometimes you have to do that because, it's a while since you did trig and it might not be your strongest suit. So let's continue with this fella. Pretty innocuous looking guy. Still the power rule. Still need to figure out how to write it. What power of x is that guy?
X to the -2.
Agreed. If this was 10, what would be the only change to my answer?
10 times x to the -2.
So do you see multiples don't do much, right? You can almost ignore them. Well, don't totally ignore them, but they don't, they don't interfere with the general process. Now this fella is going to be add 1 to the power and then divide by the new power. Do you think I'm going to leave this guy like this and plug in 4 and 1? Or do you think I'm going to do a little bit more style point first? What's your gut feeling? Leave it or fix it?
Fix it.
Okay. Are you comfortable with -10 x to the -1 is the same thing as -10 over an x? You're comfortable with that? Now, when you start plugging in the numbers, you'll see the advantage to that. -10 over 4, take away -10 over 1. This guy simplifies down to -5/2. This guy becomes +10, and I believe you finish with 15/2. With one exception, I think the vast majority of questions today have been the power rule. Just you had to do some work to be able to use the power rule. Are we good? Right, here's one to try. Oops. You got 2 minutes. Go for it. Find the area under that curve from 1 to 4. Okay, last few seconds. Some of these terms are totally okay and I don't need to do anything. And it might look like 2 terms need to be fixed, but actually only that one needs to be fixed. So I'm going to leave the x squared alone, I'm going to leave the 1 alone, and I'm going to leave the 1 over x alone. Now, if it'd been 1 over x squared or something different, I would have fixed it, but I don't need to fix it. The one that I do need to fix is this ugly 10 over square root of x guy. And I need to write him as a fractional power of x. And what will 10 over the square root of x look like as a fractional power of x?
-1/2.
Now we're ready to go. This one is add 1 to the power, divide by the new power. That's just x. Now the reason I left this guy alone is because isn't this a special case? It's the only time the power rule should not be used. And that's when it's 1 over x or 10 over x, right? Just an x on the bottom. In this case, isn't the answer the natural log of x? Now this guy is add 1 to the power and divide by the new power, which gives me that. Now some style points. This guy needs to be turned into that. Evaluated at x equals 1 and 2. Right. You plug in 2, you get 1/3 2 cubed plus a 2 plus a log of 2 plus 20 times square root of 2. Take away 1/3 of 1 cubed plus a 1 plus a log of 1 plus 20 square root of 1. Okay, let's see.
Professor, aren't we
Yes.
doing 4 instead of 2 for the x?
Oh, shooting space. Thank you. I can't read my own writing. 4 cubed 4 log 4 square root of 4, right? So, well caught. Thank you. That guy is 64/3. That guy is 4 now. That guy there is a log of 4. And that guy's 2, and 20 times 2 gives me 40. This guy is 1/3 plus 1. What number is the natural log of 1?
Is that 0?
0.
It is. So 0, I don't bother. 20 root 1 gives me 20. With the exception of that guy, I can combine all these things together, right? So I think it's time for the calculator to take over. So I'm going to go 64/3, which is this guy. Going to add 4, which is this guy. Forget about that guy. Plus 40. That's all that stuff. Then I'm going to take away 1/3, take away 1, and take away 20, which leaves me. Oh, that I wasn't expecting. It's a nice answer. It's just 44. I was expecting some kind of, 57/3 or something, right? But hey, it is what it is. 44 plus the natural log of 4. And it is okay. That is the final answer. You might think, well, I would hope to see just a single thing as my answer, but that's not always going to be the case. That is a correct answer. You don't need to do anything more to it. It's as good as it can be. Now, you could have had this written down. You see that log 1? You might have just wrote it down as log 1, didn't think much about it. You put that into WebAssign and it's going to say you're wrong. because WebAssign is clever enough to know that the log of 1 is 0, in which case that term's not really there. So just be careful. If it says you're wrong, don't automatically assume that you've screwed up and you don't know how to do it. Look for the simple mistakes first. Like, I wrote 4/8 and it should have been a half. That sounds silly, but I've done that, right? Or e to the nothing, right? I've written down 14 plus e to the 0, right? What's e to the 0?
1.
Right, so I should have said 15. Can you see how little details like that are not major problems, right? They are fixable. I mean, the hard part is doing the whole thing, isn't it? But couldn't you still come a cropper if you're not just a little bit careful about the finish, right? So try and make sure that you do style points, because you can't write down 24 to the power of half and think that that's good. WebAssign will just say you're wrong, right? You're not allowed to do things like that. Excuse me. Let's give you a weird one. Well, they're all kind of weird, but more weird than some. Let's do something that doesn't need the power rule, because I don't want us to get caught up with thinking everything's a power rule, because it isn't. A lot of them are, but not all of them. This guy doesn't need fixing. This guy is good to go. You just have to know what its antiderivative is, right? Oops. Antiderivative of 5e to the x, right? So one of the guys over here, 5e to the x, 5e to the x. Antiderivative of secant squared. Oh, can I change that to pi? Antiderivative of secant squared.
That was tangent.
Yeah, there it is there. And we're going to evaluate it x equals 0, x equals pi. 5e to the pi plus the tangent to pi. Take away 5e to 0 plus the tangent to 0. Can't do much about that guy. He is what he is. I want to check this fella. Okay. I may change that, but I'm pretty sure pi is fine. Oh. The tangent of pi is 0. Should have shown you that before I typed it in. Take away. 5e to the 0 is not what I'm going to write. What is 5e to the 0?
5.
Just 5. Can you trust me that the tan of 0 is 0, but I could have done it in my calculator. Now, what we're left with, 5e to the pi, take away 5. It's totally correct. I'm happy with that. If you want to be nitpicky, I guess you could do that. But I'm quite confident that WebAssign will agree with both those answers, so you're good. So just so we don't get caught up with everything as a power rule, there's an example of nothing being a power rule, right? Any questions? Are we good? I guess we're good. This particular one is like question 13. Looks like that guy. Do you think this one is eventually going to be a power rule? Eventually. You agree? Can you see they have a kind of look to them that you know that's what you should be getting? Right now, it's no good. Right now, it's not written in the correct form. We did one earlier today, so let me just jump right into it. Can't you just call the v squared v to the negative 2 and then distribute? Are you happy about this times this gives you v squared and this times this gives you 2v? Now I can do the power rule. Evaluated 2 and 1. 1/3 2 cubed plus 2 squared. Take away 1/3 1 cubed plus 1 squared. 8/3 add 4. 1/3 add 1. What's that going to get me? It's going to get me 7/3 add 3, which is another 9/3. So I believe the answer is 16/3. Now let's check if I can do things in my head by letting the calculator do it. So it's 8/3 add 4, take away 1/3, take away 1, and math, fractions, answer. 16/3 it is. We're good. So it's, by the time you get to somewhere around about here, isn't it probably going to be grab a calculator time? Maybe even the line before that. This is like question 12. This is not a power rule. Pretty obviously it's not. Antiderivative of 2 cosine thetas.
Is that 2 sine theta?
Agreed. And you're going to have to remember how to pronounce things. It's theta, not theta. Right?
Oh, weird. My other teachers have got that wrong.
I know. It's surprising how many Americans don't know how to say a simple Greek letter like theta. Now, I can understand how you got the English letters mixed up. You know, somewhere in your history, Z turned into a Z. Don't know why, but it did. And J turned into a J. But how on earth can you screw up another country's letter? How can you screw up theta and call it theta? I mean, what on earth happened? You know you should be apologizing to the Greeks for that. Okay, I've picked on you enough. I need to find 2 sine pi upon 3, take away 2 sine pi upon 6. And let's see if that guy's handy. That guy. If you're going to be finding exact values for sine pi upon 3 and sine pi upon 6, aren't you going to use this triangle? Right? Now the sine pi upon 3 is already calculated. You see its opposite hypotenuse is a half. So that's 2 times a half. Now what about the sine pi upon 6? Well, from pi upon 6, right, Nobody caught that. That's a 6. Pi upon 6 is a half. 1 over 2. What's pi upon 3 going to be? It's root 3 over 2. There we go. Gotcha. So they cancel out and you get root 3, and they cancel out and you get 1. So the sine of pi upon 6 is a half, and the sine of pi upon 3 is root 3 upon 2. So nobody caught my mistake. And that's the end of that guy. Now we are going to be doing exact values for areas under the curves. We're going to be doing that a lot. Not just in this section, but in the future. I'm going to leave it for a little while because we have 2 more things to do, and then we can say 5 threes over. First thing I'm going to do is look at what is sometimes called an area function. And there's only one example of this in the homework. So I'm going to go to it and we'll do this, at least my version, together. Right. Let's see what we got here. Basic 2. Can I make that a little bit bigger, probably? Yeah, that's good. Now, what does an area function do? Me personally, I would have called that A of X, for area. But they're calling it G of X, which is okay. And the area function G of X is equal to the area from 0 to X of some function f of t. So here is the zigzag function for f of t, right? And the area function G of X is the area from 0 up to whatever X is. Now, based on this definition, we are going to find most of these guys. Let's start off with G of 0. G of 0 would be the area from 0 to 0. It's a kind of silly question. What is the area under a curve if you start at x equals 0 and you finish at x equals 0?
Zero.
From 0, yeah, it's a silly answer. It's 0. Right, now the next one makes sense. G of 5. G of 5 is the area under the curve from 0 to 5. So essentially, wouldn't it be this little rectangle? Because we can get these exact values by just finding the area of a rectangle. So let's see who that is. 5 units this way, 10 units up, that has an area of 50. Okay, so what's the next one? I want to find G of 10. So 0, 5, 10. So it's here. So you can imagine a vertical line going here. And we're trying to find the area of all of this stuff over here. I would probably split this as a square and a little triangle stuck on top. The square is 10 units by 10, that's 100. And the triangle is half of 5 times 10, and half of 5 times 10 is 25. So I make that 125. Are you comfortable with how I've calculated these in my head? But you can imagine that you did some written down work and go with it. Right, now 15 is there. The area function is the area under the curve from 0 to here, right? 0 to 15. I can think of lots of different ways to do this, but let's cheat. Don't we already know the answer from 0 to 10? So can't I just find this little triangle and add it on, and that would be the answer? So I don't need to reinvent the wheel. I can use previous answers to help me with this one. So what's this extra little bit that they've added on from 10 to 15 look like? Well, it's 5 units by 20. So half of 5 times 20 ends up being 50. So that ends up being 175. Now, if you go all the way to 30, which is here, you're going to find the area under the curve for this bit, and then aren't you going to find the area under the curve for this bit? And it's the net area. What's going to happen with these areas here, starting at 15 all the way to 30? What's special about the answer to this area?
It's negative.
It's negative. So that when you get your final answer, it's going to be less than 175 because it's going to be 175, then take away 30, you know, that kind of thing. So I'm just making this up because I want you to do it yourself. But let's pretend it was that. You get 145. And you understand it's a net area, so pluses and minuses partially cancel each other out. And that's what you do with the first part. And it's kind of the only example of that you've got. Now, the next question says, on what interval of G, on what interval is G increasing? So when X is 0 to 5 to 10 to 15 to 20 to 25 and to 30, isn't the area only increasing up to one specific number? So from 0 up to what number is the area function getting bigger, increasing? From 0 up to what
15.
value of it? Agreed. Would you agree at 15, that's the end of it getting bigger? Because what's going to happen if you do 0 to 20, aren't you going to take a little bit away? And 0 to 30, aren't you going to take quite a big bit away? Right. Now, this answer is kind of really connected to that. Where does G have its maximum value? Isn't that also at 15? Because any value of X after that, doesn't the area go down? And any value of X before that, you've still got a little bit more to add on before you reach the max. Now, here's the last one, which is kind of, for a lot of people, the hardest. Here are 4 graphs of what this integral function would look like if you actually found lots of values and plotted them. But only one of these is correct. So you've top left, top right, bottom left, bottom right. Which one of those 4 is the only one that's actually the correct shape for the area function?
Top left.
First one.
I like it. First one, top left. Tell me what made you decide on that one, because it's the right answer.
The maximum is at X equals 15.
Okay. Would you agree that the maximum is at 15? And and it's a maximum that's positive as well, right? Agreed? Did anyone find a different way of picking that one rather than any of the others?
I just did like on the interval it's increasing and then it's decreasing. So all the other ones, it doesn't really reflect that.
Right. So this one decreases and then increases. So you choose that one because of its shape, for want of a better description. That's a good reason. Someone else, I heard it's a female voice, was, what was it you were thinking?
Negative, or never negative.
Okay, so you're picking it because none of the answers are ever going to be negative because of the calculations. Do you see, there's no right answer to how you pick the right graph, isn't there? Different ways of seeing the information, but they should all lead to the same correct answer, agreed? So just because you saw the top left as the right answer and the way that you decided that was different from someone else, that to me is not an issue. Isn't it still correct? Your thought process was different, but it's the same answer, so you must have been okay. So it shows you how people's minds don't always see the same thing. Okay, I need a joke. Sarah. Oh, Sarah. Have you got a joke for me?
What?
Do you have a joke?
Yes.
You do? Go for it. What you got?
Or what?
I said, do you have a joke? And you said, yes. And
Oh.
I now said, what is that joke?
I misunderstood. I don't have one.
Oh, darn it in space. Anybody got a joke for us? Lyra, you got a joke? Is it even worth asking you, Skylar? Not worth asking. Okay. Where shall I go with this? Let's do chemistry jokes. Two atoms were walking down the street and one of them stopped suddenly. He goes like this. And his friend said, what's up? He says, I think I've lost an electron. And he says, are you sure? He said, yes, I'm positive. No. Okay, that one died to death. Why should you never trust what an atom says? They all, yeah, they make up everything. God, you're a tough crowd. Lyra, you like that one. Good. Oh, Ryan, I think that's a good sign you like that one. Any other chemistry jokes? Oh, Chuck Norris does not believe in the periodic table. The only element he believes in is surprise. Oh, God, I'm working on you, Matt. I'm going to get a smile off you yet. Okay, let's try another one. What do you do with a very sick chemist? Don't know.
You helium?
Well, if you can't cure him, you bury him. You know, I was going to tell you lots of chemistry jokes, but I wasn't getting any reaction. I think I'm counting that as a smile, Matt. I got a smile. I knew if I worked on you, I'd get some out of you. Okay. Now that you've heard some of my really poor chemistry jokes, has that jogged your memory for some really bad jokes? I love to hear bad jokes. Right, Sarah, I'm putting you in the spot again. Did that help? Did it jog your memory? Do you have any jokes? No, she has a worried face. I got you. Okay. Last chance. Anybody? Okay. Let's move on then. That was a nice little break. Gave my brain a chance to settle down. Oh, maybe somebody in the chat has a joke. Okay, someone else. The last thing in section 5.3 is called the fundamental theorem of calculus part 1. You know, you wouldn't have a part 2 unless there was a part 1, right? It kind of doesn't make sense. Part 2 is very, very useful, right? It'll give you exact value of area under curve. Lots and lots of uses for that. Lots of applications. This bit that I'm going to show you is not that useful. In fact, there are only 2 homework questions. Very quick to do, and we're actually going to do them together probably in a few minutes. But let me show you what the fundamental theorem of calculus says. Imagine that you have an area function. Like that. The fundamental theorem of calculus, part 1, says the derivative of the area function is that guy. So you may say, what does that mean? Well, I'll show you. It's so easy, you will probably, at least the ones you're going to see, you are going to talk yourself out of the answer. Take that guy, for instance. You're going to be asked to find what the derivative is. Well, according to the fundamental theorem of calculus part 1, the derivative of this area function is just that guy with an x. So it is x squared plus 1 over x. And if this had to the power of 100, the answer would be that. Now, where did that come from? Well, there's a whole blinking bunch of theory for it. Actually, part 1 is how they figured out part 2. So once they'd figured out that this relationship was true, they kind of turned it backwards and it came up with this result. So it did have uses, but only in the use that this theorem generated the one that we all use. So I said there's 2 questions, and we're going to do them right now because they're really quick, and that means we can go on to the next section. Now, the guys that I've got may not be exactly the same as yours because they do change them a little bit, but at least you'll get the gist of what's going on. Okay. Here's question 2. Let me make that a bit bigger. There, maybe even one more. Oops. Nope, still good. The area function g of x is that guy. What's the derivative of g of x? What's the derivative? You're overthinking it.
Is that the square root of x squared plus x to the 4th?
Isn't that the quickest 8 points you've probably ever got in homework so far? Right, there's just one more to go. What do you mean? Oh, I'm in student version. Let me try that. Oh, shooting space. I shouldn't have tried that, should I? Sorry about that. I never. Okay. If you just hold on a few seconds, I'm going to have to go back and do WebAssign. I don't think you really want to see my password, so I'm doing it on a different screen. Okay, technical difficulties all over the place here. It's not letting me back in. I can always do it a different way if it doesn't work. Almost here. There we go. And there we go, question 2. Right. What are you looking at right now? You're looking at question 2. Are you seeing blank screen or what? I'm not quite sure what you're seeing anymore. Are you seeing, what you should be seeing is question 2 with the square root of x to the 6 on it. Are you seeing that? Okay, we're good. Right, here is question 3. Now, what did they do to make your life slightly ugly? They didn't use the variable x, they used the variable s. Can you see that that guy there just gets turned into s's? And that's the answer. So the fundamental theorem of calculus part 1 just says that the derivative of the area function is the function, right? Is f of t, with the t replaced by x. So we are now going to move on to our next section. And let's see, I need some room here. Keep this guy handy. And if you get an integral from 0 to 1 of x squared dx, that's an example of an integral, right? These kind are called definite integrals. And they are equal to, you're just going to trust me, they're equal to a number. You can check that one. You can, of course, get this guy. And when there is no numbers, no limits of integration, these are called indefinite integrals. So the next section deals with finding some of these, but mostly finding indefinite integrals. So you might think, well, how do we get an indefinite integral? Well, you've actually done a lot of indefinite integrals on Thursday. I just didn't call them that. I don't think I did, at least. So let's show you how it works. Here is an indefinite integral. You find the antiderivative. Well, that makes sense. Add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. You get 5x. Here's the difference. An indefinite integral is not evaluated because there's no numbers to evaluate it. You just add a plus c. Can you remember doing a whole load of those guys? In fact, aren't all of these indefinite integrals? So it's not that different, isn't it? Aren't you going to use power rules and all the good stuff? So what are they going to do to make your life more awkward? Well, they're going to mix and match them. So sometimes you're going to get this question and sometimes you're going to get that one. So you have to know when you get a number, when it's a definite integral, and when you stick a plus c, when it's an indefinite integral. I don't think it's that hard to tell a difference, would you agree? Limits of integration, no numbers. Limits of integration, definite integral, the answer will be a number. No limits of integration, indefinite integral, the answer is going to get plus c. So that's the first thing they're going to do. They're going to mix and match some of the questions, so you have to figure out which of the two situations you're dealing with, which I don't think is too hard to keep track of. And then the second one, they are just going to make your life really difficult by giving you harder and harder things to find antiderivatives of. So if you've thought what the ones you've got right now are difficult, you haven't seen anything yet. I'm going to just close off a window right now. And I'm going to do a view. And I'm going to start by looking at the first question. It's the integral from 0 to 1 of x (3 cube root of x) plus 5 4th root of x dx. And that question has kind of both things happening. A definite integral or an indefinite integral? What we're looking at here.
Definite.
Right. So when we're finished, shouldn't the answer be 17 thirds or something, right? It should be a number. Second thing is ugly, right? Not your usual x cubed plus 4x, right? You could do them in your sleep. Now we're moving on to the messy things. So in this case, the cube root becomes 1/3 power, and the 4th root becomes 1/4 power. Are you comfortable about cube roots give you a fraction of a third and 4th roots give you a fraction of a quarter? Are you also happy about why I did that? Why I needed to change them? Because
Power
what's
rule?
going to, say it again?
Oh, is it for the power rule?
Yeah, but I can't do the power rule until one more step. Don't I have to multiply through by x? So this guy is going to be x times that, which gets me 4/3. And the second one's going to be that times that, and that gets me 5/4. So yeah, it's a power rule, but a crazily ugly power rule. Would you agree it's not a very nice x cubed kind of power rule? Now the rules are still correct. You add 1 to the power, which is 7/3. Dividing by 7/3 is the same thing as multiplying by 3/7, and that's why that is now 9/7. The second one, you're going to add 1 to the power, which gets you 9/4. And dividing by 9/4 is the same thing as multiplying by 4/9, which is why that gets you 20/9. And it's going to be evaluated at x equals 0 and x equals 1. Now, normally I would do some style points on this. If I did do some style points in this, wouldn't the 7/3 be the really ugly looking cube root of x to the 7? And the 9/4 would be the 4th root of x to the 9. Are you happy about how fractional powers become radicals? And normally I would do that, except there's always exceptions. Would you agree that the number 1 and the number 0 can be calculated quite easily without maybe resorting to doing this? And since I'm only interested in the numerical answer, I'm allowed to do that. So if you plug in 1 here, you're just going to get 9/7 plus 20/9. And if you plug in 0 here, aren't you just going to get a load of zeros? 0, 0. And then calculator time. 9/7 add 20/9, math button fraction, and 221 60/3. And we are finito. We are finished. Now I'm going to do the same question, but as an indefinite integral to show you that there are some differences. Same line here. We would get to that line that would look like this. In an indefinite integral, don't you put a plus c? So that's a pretty major difference, right? Right, there's no values, so it's a plus c. But style points tells me that this is not a good version of the answer. Would you agree? One of the rules of style points is make it look like the original. So in this case, I can't avoid turning this into the cube root of x to the 7 and the 4th root of x to the 9. So that's what the answer would look like as a definite integral and now as an indefinite integral. And by the way, that one's very similar to question 1 in the homework. Any questions about this pair of questions?
Yeah, I just have
Bill.
one question real quick.
Mm-hmm.
So when you change the root 3 to x to the 1/3, where did the 4/3 come from? Because then we didn't.
Oh, so we've got 1/3, right? Then
Yeah.
I do the power rule. So you add 1 to the power. Well, we don't write it as that. That's where the 4/3 came from.
But then we went down to 7/3 as well. Was that just?
Oh, that's because the answer had an x times it as well, right? There was an x
okay.
out here, and the x added another 3/3.
Okay,
And
that
that's
makes
why
sense.
that
Thank
became
you.
a 7/3. Right, that's where that came from. Let's get your brain moving. Let's do an indefinite integral. And we're going to do the dreaded trig questions. Of all the questions in the world that are probably going to cause you the most amount of trouble, it's probably going to be trig. Because there are lots of things you can do with trig functions, like change them into other things and so on. Would you agree that this integral hasn't got a chance in Hades of being done right now? It's just not got anything even vaguely like, if I can go back to my guy, it's got nothing in here, in particular round about there, right? It maybe have the pieces, but it doesn't have all sorts of other pieces mixed in with it that stop us being able to use it. So there are two distinct algebraic ways of dealing with this same question. Both are valid. You can use whichever one your brain thinks makes more sense to you. And it doesn't need to make sense to anybody else, only needs to make sense to you. So let's look at this guy. Top row. Do you notice that they both share a common factor of 5 sine theta? So if I pull that out, I get that. Are you okay with that? A 5 sine theta in both terms? Now the next step is just knowledge. Things that you should have seen somewhere in trig. It's been, whatever, a year since you've seen it, 6 months, whatever. And hopefully it's still in there. You might have to shake the box a little bit, but it's going to fall out. What does 1 plus tan squared equal?
Secant theta.
Secant squared theta. Which means these two can cancel. Can you remember trig identities where you turned a trig expression into some other trig expression, typically a simpler one? This entire ugly fraction, believe it or not, is just the same thing as 5 sine theta. Now, would you agree that guy's easy to do? I mean, I can integrate 5 sine theta. Which version of 5 cosine theta is the answer? Is it plus or minus?
-5 cosine theta.
And if you type that into WebAssign, you would be marked as wrong, not because of what you said, but because of what I haven't written down yet.
Plus a constant.
Yeah. And someone in the other class has said to me, I don't know if this is true, but let's assume it is. Will you make the plus C a capital C, not a little c? Because the person said that WebAssign, believe it or not, didn't like the little c. I think that's what she said. So when you're doing all the indefinite integrals with the plus c's on them, will you just make sure it's a plus capital C just to keep WebAssign happy? right? I don't know why it wouldn't take little c, but evidently it doesn't. Right, does that make sense as long as you remember that 1 plus tan squared is secant squared, right? That process. Now I'm going to show you a much uglier process. The only advantage that this second method is going to have is that this is like what you do if you can't think of anything else to do. If you've got a trig expression with sines, cosines, secants, tans, all that stuff all jumbled up, and you're looking, you're saying, nope, nothing's coming to mind, then what you can do is turn every single guy into a sine or a cosine that isn't already a sine or a cosine. So it's going to be 5 sine theta plus 5 sine theta. Isn't a tan a sine over a cosine? So won't a tan squared be a sine squared theta over a cos squared theta? All over. What is a secant in terms of a sine or a cosine? It's a secant theta. (50-50) chance. What's a secant?
Is it cosine over sine?
That's a cotangent.
Yeah.
But nah, at least you tried. I like, you have a shot. You might want to go back and look at some of the trig identities, right? What things can be turned into. So for instance, a cosecant is 1 over sine theta. A cotangent is cosine theta on the top over sine theta in the bottom, right? Secant squared theta plus 1 is tan squared theta, right? Things like that, so that you can manipulate these better. If you're a little bit rusty, you might want to go looking for those. Maybe write them down on a little card and have them close to you when you're dealing with these questions. Now, this gets uglier before it gets nicer. This is a fraction. This is the top. Oops, that's good. This is the bottom. Can't you take this multiplied by the reciprocal? And if you do, you get 5 sine theta plus 5 sine cubed theta over cos squared theta, just combining those, times the reciprocal, which is that guy. And cos squared times the first one gets you 5 sine theta cos squared theta. And something nice happens. Isn't this fraction times cos squares? Don't the cos squares cancel? And you're left with 5 sine cubed theta. So everything has been turned into sines and cosines, and the original has become this. This is going to take us a lot longer than the other one, but it is eventually going to work. Can you see any common factors that we could pull out?
Five sine theta.
I agree with you. Now, if you pull it out of here, you're left with a cos squared theta. If you pull a 5 sine out here, aren't you left with a sine squared theta? Almost there. What's sine squared plus cos squared theta? Sine squared plus cos squared.
1. Is it just 1?
So 5 sine theta times 1 is 5 sine theta. Do you see we're back to where we were in a much longer way? If you can see some trig identities like 1 plus tan squared is secant squared, if you can see them, and this will work really quickly. If you don't see it or whatever, this approach, if you hang in there, turn everybody into a sine and cosine and just keep working on it, you know, pulling out common factors, combining things, whatever it takes, it should hopefully eventually get you to the same destination. But what, the scenic route, right, the long way around, but you got there in the end. Agreed? Now, if I stuck a 0 to pi upon 2, wouldn't this question now be, whoops, pi upon 2, wouldn't this question now be a definite integral? But wouldn't all of this be the same working? So the algebra does not change just because it's a definite or indefinite integral, right? You still do the same stuff you would have done. And the number thing really doesn't happen until the last couple of lines, right? The numbers don't matter at all until then. And you could almost ignore them. Any questions about that ugly one? Because it is an ugly looking trick one. Okay, we still got time. Let's see what I got on my little list. I like this question so much. Nobody else likes it, but I like it. It's a definite integral. Right? But even if it was an indefinite integral, it would still be the same horrible question, right? You look at these questions and you're mostly going to think this guy is going to be some kind of power rule eventually. And you'd be wrong in this case. There are always exceptions. This is one of them. So I got to figure out something else to do. In particular, do you notice that t to the power of 4 minus 1 is an unusual difference of 2 squares? Try it out. Check that. Doesn't it work? So t to the 4 take away 1 is actually a difference of 2 squares. T squared plus 1, t squared minus 1. Now the good news. Won't that cancel with that? So that means this question now becomes that guy. We can get the antiderivative, right, of that guy. We can get its integrals, another name. Inverse tan. Evaluated at t equals 1 and t equals square root of 3. That becomes the inverse tan of root 3. Take away the inverse tan of 1. And I bet you I've thrown that damn thing away now. I'm looking for my right angle triangle. I think it's gone. Yeah, it's gone in that one. Is it in here? Okay. If you look at the two triangles, this one here, what angle has a tangent to root 3? And this one here is what angle has a tangent to 1? This one we did earlier, it's pi upon 4. Does anybody remember what the inverse tan of root 3 is? What angle has a tangent of root 3? Any takers?
Is that pi over 6?
Pi over.
Yeah, you were so close. I mean, you almost got it. Pi upon 3. And that guy ends up being, what's that? 4 12s take away 3 12s. So I guess the final answer is 1/12. And what would the answer look like if it was just an indefinite integral? The answer would just be inverse tan of t plus a c. It'd be a lot quicker to do. It'd just be that guy with a plus c. Give me a few moments to digest that. Are we good? Good. I'm using up all my paper. I'm going to have to charge you money. Actually, college gives me all the paper I want. Okay. For the last 10 so minutes, let's just look through what these questions look like in the homework. Okay, look at question 6. I'll make that bigger. That looks kind of a little bit awkward. There. Find the general indefinite integral, right? In other words, find the guy with the plus c. You don't need to tell me the details, but what method would you use to get question 6?
Are you asking like the power rule?
Yeah,
for example.
that's exactly.
Okay.
Yeah. So wouldn't you just add 1 to the power, divide by the new power? Would you agree it'd be downright ugly numbers, decimals, and so on? But that's not your fault. If the answer is ugly, it's because the question was ugly. But you would just add 1 to the power. So what would that be? 2.4? And then 1 over 2.4. Try and make it as pretty as you can, but you can't really do too much with that. Would you agree that this one is so straightforward, you might talk yourself out of the right answer? Isn't this power rule good to go? Don't need to do a darn thing. You agree? Power rule, just got a variable u, I guess. 4x squared is a power rule, and so is plus 7 a power rule. But what is 8 over x squared plus 1's antiderivative?
Is that 8, 10?
Yeah, 8 inverse tan. Agreed. 8 inverse tan, or arctan if you do. I refuse to call things arctan. America's the only place in the world that even uses that archaic. You know, arctan used to be used because printers couldn't do subscripts very well. I think, like 100 years ago, something ridiculous. Everybody calls it inverse tan now. Do your physics guys use inverse arctan, I should say, instead of inverse tan? Engineers, is it inverse or arc? What do you use? Don't know.
Haven't made it there yet.
Haven't made it there. I hope you use inverse. You don't want the rest of the world laughing at you, do you? Where they say, oh, look at this funny American engineer, A arctan pi. What the heck is he talking about? Oh, he means A inverse tan pi. Why didn't he do it? Okay. Whoa, look at that guy. Definitely not a power rule. Wouldn't you have to multiply everything by secant? So you're going to get 2 secant squared plus 3 secant tans. So here's my question. What's the antiderivative of 2 secant squared? Antiderivative of
tangent.
2. Sorry, say again.
Is it 2 tangent?
You nailed it. And the other one, I don't think we've done a question like this yet. What is the antiderivative of 3 secant tans?
3 secant?
Yep. Yeah, it wasn't that bad, right? As long as you remember those guys. Would you agree that one's got nothing really going on about it? Oh, this one will test you because I don't have it in front of me. Question 11. I don't like dr. I like to stick the dr at the side. So I would have called this 1 over the square root of 1 minus r squared dr. That's how I would write it, but that's the way they've written it, and it's the same thing. What is the antiderivative of 1 over the square root of 1 minus r squared? That is in my list. One over the square root of 1 minus r squared.
Inverse sine?
You nailed it. Inverse sine it is. That table of standard integrals is going to be like your Bible, right? You are going to memorize it back to front, upside down, standing on your head, because those are the guys that are going to make your life so much easier. Because if you can recognize it, isn't this question a one-liner? And if you can't recognize it, aren't you just going to stare at it and get frustrated? So you got to know the standard integrals, right? Things like that, because those are going to be your bread and butter type things that are going to get you through trouble. These guys here are all applications, and I don't want to talk about applications today. So we are going to return, and I am going to give you the ugliest looking indefinite integral I can think of. And you are going to get it right. That's your challenge. And that's after 1 hour and 50 minutes of listening to me. So you poor souls, your brain is already half sponge. So you ready? The ugliest antiderivative I can come up with. Now, not all the PCs are going to be ugly. You got 3 minutes to do that, guy. It's a little bit of A, a little bit of B, a little bit of C. There is no, there's no major algebra necessary. But if you look at it, don't 2 of them need to be fixed before you can use a power rule? And that's the only clues I'm giving you. And starting from now. Last 30 seconds. Okay, let's go for it. I'm going to change this guy into a fractional power and this guy into a negative power. And this is negative 1/3. And this one is negative 3. Do you see there's a difference between a cube root and a cube, right? Now, they're now ready to be converted. Add 1 to the power and divide by the new power. Negative 1/3, if you add 1, gets you positive 2/3. Dividing by that is the same as multiplying by 3/2, and 3/2 gets me, I believe, 12. Did I do that right? I don't see too many nodes. Did I screw that up? No. Did I? I did. I did. It's 12/2. There. Does 6 look better? Now I see nodes. So let's move on. Isn't this one over here? And the antiderivative of secant tan is just a secant because it is. And 5e to the x is 5e to the x because it is. Right, it's over here. So those two were just, if you got a good memory, you just write the answer down. Won't this one be add 1 to the power, which is now negative 2, right? Negative 3 add 1 is negative 2. Divide by the new power. I believe that gets you a +2, doesn't it? I've got a couple of nodes, so I'm using that. And the 1 gets me an x, and then you go add c at the end. Would this question qualify as the finish, or do I have some style points, at least for a couple of them? You agreed? Doesn't this have to be fixed? And this one here has to be fixed. So your ultimate, definitely finished answer is 6 cube root of x squared, which is this guy. And 2 over x squared. Boom. None of your homework questions will be as big as that.